Hey, hi friends, this is Varun Gowda. Welcome to my YouTube channel. Today we'll discuss about tokenization. Let me take an example. Let me take an example here. We have an we have an we have an LLM model here for which we are giving input as, let's say, I like chat GPT. We are giving this sentence as an input to this LLM model, and we are expecting an output from this LLM model. Correct, right? But this LLM model this LLM model or any language model don't have any idea of what these words are, what these words are symbols means. Because this LLM models, if you are giving input as I like chat GPT as an input sentence to this LLM model directly, these LLM models or any language model don't have any idea of what these words or symbols means, because these LLM models or any language model understands only numeric values. Correct, right? If you give directly input like I like chat GPT to this LLM model or any language model, they don't understand, because they understand only the numeric values. Correct, right? So what we have to do before feeding this input to LLM model, we have to convert this into numbers. Means we have to convert this into numeric values. Correct, right? How we gonna convert this into numeric values? Correct, right? Let me write this example again here. I like chat GPT. This is what the input sentence we took for the example, right? We have to convert these words in this sentence to numeric values. How we gonna convert? We will convert the words in this input sentence to numbers using the technique called tokenization. What happens in tokenization? Let's take, this is our input sentence, right? Let's say we have a tokenizer. We have a tokenizer. Tokenization is done by tokenizer. Correct, right? Consider we have this input sentence and we have the word I like chat GPT. Correct, right? What this tokenizer does, it will take every word in this input sentence. Here I is one word. Let's say this is word 1, this is word 2, this is word 3, right? What it does, it will take each of these words and convert into tokens with associated token IDs. Let's say the word I is converted into one token with associated token ID as 111. Similarly, like is converted into one token with associated ID, let's say 112. Similarly, chat GPT might have been converted to two tokens, chat as one token and GPT as another token. We'll see how these words are converted into tokens and why this one word is getting divided into two tokens. Correct, right? We'll see in our later stage of this video, but as of now, consider this is converted into two tokens. Let's say chart is converted into another token, and with the token ID, let's say 113. Similarly, GPT is converted into another token with token ID, let's say 114. Now, how many words we have in the input sentence? We have 3 words, but those are converted to 4 tokens with their associated token IDs. Correct, right? Now, each of these words can be represented with token IDs, right? Where these tokens and where these token IDs will be available, we'll see in this session in the later stage. You got it, right? The tokenization means the process of converting the words in the input sentence to tokens with their associated token IDs. This process is called the process of converting input words into tokens and their associated token IDs. This process is called tokenization. And how does this process will be done? Using the tokenizer. You got the definition, right? The process of converting the words in the input sentence to tokens and their associated token IDs. This process is called tokenization. Then how are we going to implement this tokenization, right? Mainly there are three ways. Mainly there are three ways. What is the first way? First way is word level tokenization. The second way is character level tokenization. Character level tokenization. Third way is subword level. We'll see what each of these ways are. Just I'm writing here. We have three ways. Correct, right? We'll discuss about this word level tokenization now. We'll discuss about word level tokenization. Let me write it here. Word level tokenization. Word level tokenization. Let me take one example here. Consider this as word level tokenizer. This word level tokenizer, for which we are giving input from multiple English data sources. Here the data source can be anything like English dictionary or websites, or let me write it here, websites having information related to movies, actors, some articles related to technology. Like this can be from any of the website related data, not only with respect to movie, actor, articles and technology. It can be related to any domains. Let's say it can be e-com related, it can be retail related or medical related. It's a huge data, right? We are getting the data from multiple data sources and putting it to this tokenizer, and this tokenizer is having some let's say some set of rules, or I can say it's having some algorithm. What this set of rules or algorithms does, it's going to take input from this different data sources, and it's going to store each of the words it's going to see in its, this is called vocab. This is word level tokenizer vocab. What it does, it will assign the token ID. Let's say the token ID is T1 for the word 1. Like that, it will assign till n number of words with the n number of token IDs. Correct, right? Each word is converted into one token with associated token IDs. Let's say this is token 2, which having token ID 2, and token 3, token 4. Continue till token n. How many words it can able to see from this input data? Those many tokens will be there. This word 1, word 2, word 3, word 4. Like that it will continue till n. Correct, right? They are feeding huge amount of data, right? Of course, this vocabulary size now is it's a huge size vocab. Correct, right? It's a huge size vocab. Correct, right? Let's say, okay. Uh, let me take our input sentence. What we are using. This is what our input sentence is like. I like chat GPT is our input sentence. Correct, right? Let's say this is during the training phase, right? This is the tokenizer training phase. Now we are giving the input sentence to get the tokens and associated token IDs for this input sentence. If you give I to this tokenizer will search in his vocab. What is the token? Is this token is available for the word I? The token is available or not? Yes, token is available. It will return with the token ID. Let's say for I, we share the token ID 111, right? Similarly, it will go and search for like. For like also, it's have the token ID, and for like also it will return let's say token ID 112. Correct, right? Now again it will set for chat GPT. We are going to the word level now. So I'm passing the entire word. It will pass chat GPT. So it can able to find the chat GPT and you will get the token ID. Let's say 113 for this token ID. I'm taking this token IDs randomly. For example, this is not the actual IDs. Just I'm taking for example purpose. Correct, right? Let's consider this training has been done 6 months back. 6 months back, we took this much data and we have done the training. During that point of training, all these words are present. I like chat GPT and all. So we can able to get the token IDs for these words. Correct, right? Let's say, we have like there is one new company in the AI field established. It's a startup. Let's consider it's a startup company established 3 months before. The company name is, let's say, Build AI, and you are giving an input like to this tokenizer. You are giving an input for getting the token IDs. Let's say I want to know about Build AI, Build AI company. Correct, right? This is your input now. You are giving this as an input to the word level tokenizer. What this tokenizer does, this tokenizer takes this input I and it will search whether this word token is available in its vocab. Yeah, it's available. It will give the token and the token ID. It will give the token and their associated token ID for this word I. Similarly, for I also it will give want also it will give the token and associated token ID. Because these kind of words it has seen during the training stage. For this also will get, for this also will get. These are all the normal words, right? But this build AI word, single word build AI combined, might not be present during the pre-training stage, right? Not pre-training, during the training stage of this word level tokenizer. Correct, right? During the training phase of this word level tokenizer, this tokenizer didn't solve. For this, it might give unknown token and the ID. Correct, right? If you use this, let's say this is one word, 2, 3, 4, 5, 6, 7. Out of 7, we have one unknown token ID correct, right? Token and the token ID. If you are giving this kind of information, when you're giving this to LLM model, each of these will be converted into embeddings, right? We'll see about what are embeddings, how these embeddings are generated. As of now, consider each of this token and token ID is converted into embeddings. And if the token ID and token itself is unknown, this embedding which we are going to get before feeding into the LLM model is also unknown, right? If you give this kind of unknown embedding to this LLM model, here we have one unknown embedding, right? If you are giving this one unknown embedding along with some known embeddings to this LLM model during training phase or during the inference phase, this LLM model can't able to predict or train or learn properly, right? Because here the information which we are giving is not of good quality, right? Here we are having the unknown embedding or unknown token, correct, right? It couldn't able to learn or inference properly. It couldn't able to it couldn't couldn't able to learn or inference the model properly, correct, right? Then this word level tokenizer have two disadvantages. The first one is, as we see, if the tokenizer is trained before and new word comes, because new words keep on coming with respect to technology or medical field or anything, right? If it didn't saw these words before, it couldn't able to give the token ID and the token for that word, right? So there is a chance we might get the unknown token and ID, correct, right? Similarly, we have another issue like in this word level tokenizer is like vocab size is huge size of okay, because you have to save each and every kind of word, right, from different domains and all. The vocab size is also huge. Then what's the solution? And the second way which we saw, which we listed here, is character level tokenization, right? Okay, we'll see now character level tokenization, whether this character level tokenization overcomes these two problems or it has any other problems. We see about character level tokenization. What this character level tokenization does, let's consider we have this character level tokenizer here, character level tokenizer here, and it's having its own vocab. If you what this character level tokenizer does, whatever the input you give from multiple data sources, correct, right? Each like it is from English vocabulary itself, right? Whatever the input you give from any technology or domain, it should be formed with English alphabetical letters, right? So this vocab size, the maximum will be the vocab size maximum will be, let's say, considering some special characters and all, it will be 100 to 300. Just I'm taking the range. It can't go behind this, right? Because whatever the words that are coming in the input, it can be mapped using this all the alphabet characters, right? Let's say this vocabulary is having A to Z small letter and A to Z capital letter and some special characters. Including all these, the vocab size can be maximum 100 to 300, and whatever the input words or whatever the input data we are getting from the multiple data sources to this tokenizer, this is This is character level tokenizer. Correct, right? This is character level tokenizer. Whatever the input we are getting, this character level tokenizer can form this input sentence using the alphabet letters, right? Because here each character is a token. Each character is a token here. In word level tokenizer, each word is a token. Here each character is a token. Here the issue, the first issue, which is of vocab size is solved, right? Here in the word level tokenizer, the vocab size is huge, but here the vocab size is not huge. It's a small vocab. It's having small vocab, right? And the second issue, the unknown token, correct, right? Whatever the input you give, correct, right? It can be formed with the alphabet letters, which we have in alphabet letters with some special characters. It can be formed with this vocab, whatever the input you give, because this is at character level, right? So the second issue of unknown token is also solved here, because each character is a token here, correct, right? Here each character is a token. Whatever the input you give, it can able to get the token for that. For example, this, let's say this build AI is not a present of input data set when this character level tokenizer has been trained, but this build AI can be formed with alphabet letters that we have in the vocabulary, right? Here each word, in the sense each character is a token. BUILDAI, these are all alphabet letters, right? Each character is a token here, so that we can able, we are not going to get unknown token, right? Whatever the input you give, it can able to form that word or sentence using its vocabulary, correct, right? But let me write this sentence again here. Let me take this the input sentence. What the input sentence we took for the example is I like chat GPT, right? We took this example. If you go at word level, what is the token? Token size? It will be 3 tokens. Correct, right? It will be 3 tokens. If you go at character level, how many tokens will you get? I for one token, L for another token, I for again the next token, and K is the fourth token, E is the fifth token. Like that, we will be having another 7 tokens: T6, T7, T8, T9, T10, T11, T12. Correct, right? We have 7 plus 5 plus 7, 12 tokens. Here, the same sentence is represented by 3 tokens. Now it becomes 12 tokens. Correct, right? Let's say you are given this input to an LLM model. It has to generate the next word, right? It has to generate the next word. It has to generate the next word. How does this LLM generate the next word? Is, let me write this sentence again. I like chat GPT, right? There is one mechanism inside this LLM model called attention mechanism. What does this attention mechanism does? It tries to take this latest token, in the sense the last token, and it tries to put all the information which is previous to that. Let's say this is the previous words, right? What it does, it do some kind of operation. This is having one embedding, right? This is having embedding 1. We'll talk about what this embedding involves. Consider after these words are converted to tokens, these tokens are converted into embeddings. Now we have embedding for each of these words. What this attention mechanism does, it takes the embedding of E and it does some operation with its previous embeddings depending upon a context window size. Consider here the context window size is 2. The sense when it's predicting the next word, it has to consider the previous two words to that word to generate the next word. So what this ChatGPT, like this ChatGPT embedding has done some operation. We'll see what this operation and all when we are discussing about attention mechanism in our next sessions. As of now, consider we are doing some kind of operation with their previous tokens or else their previous embeddings. This is the embedding for, let's say E1 is the embedding for ChatGPT. This goes under some operation with E2 and E1. Let's consider this is operation 1, this is operation 2. Total operations now we have is, let's say, 2 operations with 2 tokens. Just I'm taking an example here. It's gonna do 2 operations to generate the next word. Correct, right? Here we are doing the 2 operation if you go at word level. If you go at token level, how many tokens we have? We have 12 tokens. And it's going to generate the 13th token as an output. This is next character. Next character, right? Because it's a character level tokenizer we are using. And this LLM model is going to, because each token or each embedding which we are giving to this LLM model is a embedding for character, right? It's going to generate the next character. Correct, right? If you see, in order to generate the next character, it has to do, let me write here, I like chart GPT. T is our T is our T is our last token now. Instead of chart GPT now, we are going at character level tokenizer. So our last token is T. This T should have done some operation. The embedding of T should have done some operation with all the other character tokens which we saw before. So it can encapsulate all the meaning from these previous words into the token previous characters into the token T so that it can generate the next character or token. Correct, right? Here how many operations this T is doing with this previous tokens? Let's say we have our T is 12th token, right? It has to do 11 operations. I'm just taking an example. Total operation here is 11 because this has to done some operation with this, all these tokens, right? According to attention mechanism. Correct, right? According to attention mechanism, it has to do some kind of operation with all the previous tokens depending upon the context window. What is context window means? Context window means how many tokens it should look back when it's going to predict the next word or next token. We'll talk in terms of token now because each piece of input which we are giving to the LLM model is a token now. Correct, right? In order to predict the next token, this T token has to do some kind of operation with all other tokens which is previous to that. Here I is one token, L is one token, again I is one token, K is one token, E is one token. Like that we have 11 tokens, it has to do 11 operations. Compare this word level tokenizer in the character level tokenizer mechanism if used for the LLM model for the prediction. In order to predict the next word, it does 2 operations if you go at word level. But here, in order to predict the next character, because it's a character level tokenizer we did, right? We use the character level tokenizer here. In order to predict only the next token, which is of character, it has to do 11 operations. Input data is same, but it has to do 11 operations. Here the problem, the first problem is vocab size is solved and second problem of unknown token is solved, but it comes up with new problem like high compute. It needs high compute compared to word level tokenizer, right? because it has to do more operation in order to predict only the next character. Correct, right? This is the disadvantage of character level tokenizer. Then what is the solution? What is the next way is the subword level tokenization. Correct, right? We'll discuss about subword level tokenizer now. The third way is subword level. Correct, right? Let's say we have this subword level tokenizer here, which is of subword level tokenizer, and it is having its own vocab, and it is having some, as I said previously, it is having some set of rules or algorithm, and we are giving the same input data from multiple data sources to this subword level tokenizer. How does the subword level tokenizer stores the data? Let me take this example. Let's say we have words like small and smaller and smallest, and similarly we have few words like thick, thicker, thickest. Let's consider this is the input words it saw in the input data. If the word level tokenizer has to store this input data, what is the vocab size? Vocab size will be 6, right, for word level tokenizer. But if you go at character level tokenizer, this size can be reduced. We'll see how this subword level tokenizer stores the data. Consider we have this vocab, right? We have this vocab. Consider this is the same vocab. When you give this input data, it will check for the patterns inside the data. Correct, right? Let's say the small, it will add the small as an T1 token to its vocab. And when you see the word smaller and smallest, it will learn like using the small which is already there, we can form the smaller and smallest word. If I add a token something like, if I add er, it can form smaller. If it add est, it can form, let's consider this is t2, this is t3. Already small is available. If I add a token er, it can be formed the smaller. The same if you add est using the small already available token, it can form the smallest. Correct, right? The T4 token, it is not, nothing is available in this in this vocabulary like a thick, right? It will add, let's say, thick to its vocab. But when it saw the word thicker and thickest, it has already seen uh, these words, right? Thick, smaller and smallest. For these two words, it already have this token er and est. So what it does, instead of adding er and est again to this vocab, what it does, it will see like thick is already there and er is also already there. So this thicker can be and thickest can be formed using the existing vocab. Now the vocab size has been reduced to 4. Correct, right? So whatever the input data it's going to see, it's gonna split at subword level so that it can reduce the vocab size, and it can form any new word. I will explain how it can form new word. But here the vocab size got reduced, right? If you see in GPT-3, the vocab size is around 50k. Correct, right? If you go at word level, it can go up to any number, right? But in GPT-3, using this 50k subword level tokens, we can form any of the word. I will explain how it can form the word BDI, which is a new word, right? Which is not a part of training data, but still it can able to generate a token for that word BDI. Here, the first issue of vocab size, first issue of vocab size. is solved. Correct, right? Because if you do the subword level tokenization, you can limit your vocab size by checking the patterns inside the words and having the tokens at subword level. Correct, right? Now we'll take this example for which we got the unknown token, right? If you got word level, I want to know about build AI company, right? It has to know about, you want to know about build AI company, and you are giving this sentence as an input. Correct, right? And you have trained this tokenizer, let's say 6 months back, and this never saw this word build AI. It has shown this word and it might be present in its vocabulary, and we are getting a token as T1. This is for token 2, we are getting token 3, token 4, and this is token, let me not write it now, and it comes to the word build AI. Correct, right? Comes to the word build AI, but this tokenizer never saw this word build AI, but it has shown this word separately. This is as one token, this is another token. So what it does, instead of giving a token at word level build AI, what is done, because AI is already available before 6 months, right? The word AI is already available, and build is also already available. It's something a normal English kind of word. So what it does, it will give T5 token for build and T6 token for AI and T7 token for company. Now we have the token at subword level wherever it's gonna have. Correct, right? Now we are not getting any unknown token. All the tokens which we are getting are the known tokens and having some value, which is having some meaning, Before what we gonna get, we are getting the unknown token, right? But it's having some value which is encoded as some meaning, inside which it is having some meaning. Correct, right? So if you give this kind of information to the LLM model, of course after this tokenization we have to convert this into embeddings. Let's consider we converted it to embeddings and feed it to the LLM model, so that LLM model is able to learn or inference properly. Correct, right? Here the second problem of unknown token is also solved, and if you see the problem that we got at the character level tokenization, the high compute power. Correct, right? Let's say if you give this sentence to the LLM model and it has to generate a next word, it need not to go at character level. It can go at subword level. Here we don't need, let's say in order to predict the next word, it has to do some operation with AI, some operation with build, some operation with about, and some operation with known, some operation with want, and some operation with I. If you go at character level, you would have done more operations, right? At character level. Now it's gonna do some operation, let's say some 6 operations. Correct, right? Instead of doing 20 operations at character level, we are doing 6 operations. Here the compute needed is also less, right, compared to the character level tokenization. So the best way to do the tokenization is subword level tokenization. This is the best way to do. Correct, right? Yeah, I hope you understand the session. If you like the content, please subscribe to my channel. Thank you. We'll see you in the next video.